All right, let's take a look at Lewis structures, also called electron dot structures. And these structures show the electrons that are on the outside of atoms and the ones that are being shared as a covalent bond. So the hydrogen atom over here, it's just an atom, it's not a molecule. And so for just an atom, we show the valence electrons. Hydrogen has one valence electron, we would just draw that as a dot. It doesn't really matter which side of the hydrogen you draw it on. The oxygen has 6 valence electrons. So we would draw one on each of the 4 sides before we start doubling up. And again, it doesn't matter which of the sides has the pair and which of the sides has a single electron. It's just that it should look like this with 6, 2 of them as pairs, or 2 pairs and 2 singles. Nitrogen has 5. So we would have 1 on each side and 1 doubled up. Again, it doesn't matter which side is doubled up. Here's a few more for us to try. Calcium has 2 valence electrons, so we need 2 on different sides of the calcium. It doesn't matter which side. When these 2 valence electrons are gone, calcium really has no valence electrons left, and so we would just kind of draw that as calcium with no valence electrons, and sometimes we put brackets around it to keep the charge kind of separated from the atom itself. Let's take a look at this with bromine as well. Bromine has 7 valence electrons, so 3 of the sides of bromine would have pairs and 1 would have a single. When you have a bromide ion, it would have 8 valence electrons, so all the sides would have pairs, and then we have the charge outside of the brackets. The sulfide ion also has 8 valence electrons. Sulfur itself has 6, but when you have a -2 charge, it has 8. And carbon has 4 valence electrons. This is part of what makes carbon so flexible. You can tell that it's ready to share lots of electrons and form lots of bonds. So ionic compounds are not drawn with a line in between the elements because they are not sharing electrons. You can just show the ions sitting next to each other. When you draw a covalent compound, you draw a line showing that there is a shared pair of electrons. So for sodium chloride, we have sodium ion. Sodium usually has 1 valence electron. When it's a cation, that valence electron is gone. Chlorine normally has 7 valence electrons, but when it forms the chloride ion, it has 8. And we have a negative charge. And these are just sitting next to each other, they're not bonded together. The calcium ion with a +2 charge is missing its valence electrons, so it doesn't have any. The chloride ion would have 8 valence electrons, and we would draw that twice. Here let's show a water molecule. Oxygen has 6 valence electrons, hydrogen just has 1. You can probably see that we have an opening here for a shared pair and an opening here for a shared pair. Let's draw hydrogen in a different color. So we could see hydrogen and its 1 electron, this other hydrogen and its 1 electron, and oxygen's 6 electrons are in blue, but when they come together and share, oxygen now is surrounded by 8 electrons, which is what it wants, and hydrogen is too small to want 8 electrons, but it does want 2 electrons. So hydrogen is happy and oxygen is happy, whereas neither one of them were quite as stable or happy alone. This shared pair of electrons can be drawn as a line. Sometimes that makes the structure easier to figure out, especially when it gets larger. And then the electrons that are only sitting on oxygen, not being shared with any other atom like hydrogen, these are called lone pairs because they are the lone property of the oxygen atom. They're not being shared. Here we have carbon with 4 valence electrons. Let's go ahead and bring in 4 hydrogen atoms. And this would be the structure here. This compound is called methane. Here I've started this one with 2 carbon atoms. This carbon is in green with 4 valence electrons. This carbon is in blue with its 4 valence electrons. I've started sharing a pair between them already. Now I'm adding 4 hydrogen atoms with 1 valence electron each. So the hydrogens are all happy. They all have access to a pair of electrons. Each of these carbons is not quite happy because it only has access to 7 instead of 8. We can solve that by having a second pair of electrons get shared. If these 2 single electrons move into the middle, and we can have a little bit more sharing take place. Now we have 4 shared electrons between these 2 carbons, 2 pairs, and that makes a double bond. We can draw this like this to show that there are 2 pairs of electrons being shared, or 4 electrons. And then we can draw 1 line leading to each hydrogen because there's 1 shared pair going to each hydrogen. Okay, let's start out with these 2 carbons, each with 4 electrons, 4 valence electrons, and sharing 1 pair. Now I've brought in 2 hydrogens, and the hydrogens are complete. They have 2 electrons, that's all they can fit. But these carbons are not quite complete yet. They don't have 8, they each only have 6. So you can probably tell that we want to share this pair and also this pair. So I'm going to draw that as 3 shared pairs of electrons, or 6 electrons being shared between these 2 carbons. So if you see that this carbon has access to 2, 4, 6, 8 electrons, and this carbon also has access to 2, 4, 6, 8 electrons. And the hydrogen has access to 2 electrons. So everybody is happy with the amount of electrons that they have. And this is the structure of that compound. You can draw it with the dots instead if you like, but for me it's a little bit easier to see with the lines. So as you draw these Lewis structures, you will see these general trends for some of the common atoms that you will see in these compounds. So since each atom is trying to get 8 electrons, except for hydrogen and helium, they want 2 instead of 8. Since hydrogen has 1 valence and wants 2, it tends to form 1 bond and have no lone pairs on it. Carbon starts with 4 but wants 8, so it will form 4 bonds and have no lone pairs. Nitrogen starts with 5 and it wants 8, so it only needs to form 3 bonds and then it will have a lone pair left on it. And oxygen starts with 6, so it will tend to form 2 bonds and then just have 2 lone pairs on it. So this pattern is a good one to remember. You can double check after you've tried drawing a Lewis structure and make sure that you see these types of things. Then that is a good indicator that it's a very stable Lewis structure. So for some of the smaller structures that I was drawing above, just drawing the atoms with their valence electrons and then putting them together is a simple enough way to do it. If you have several atoms in the structure and the Lewis structure is seeming a little bit complex, we have a more ordered process for drawing Lewis structures. The first step is to determine the total number of valence electrons that you are going to use in the structure. So this involves counting the valence electrons of the atoms that are in the structure, and if the overall structure has a charge, like a polyatomic ion, you will need to add more electrons to bring it up to that charge, or subtract if it's a cation. The next step is to draw a skeletal structure, one where everything is connected by single bonds, and maybe drawing a fairly symmetric structure. So if you have 1 carbon and 4 chlorine, go ahead and put the carbon in the middle. So try to make it symmetric, or put the least electronegative element in the middle. Then that has used up some of the electrons. The electrons that you have left, put as lone pairs around the outside atoms, the terminal atoms, and complete octets for those atoms, put enough lone pairs to give that atom an octet, except of course if it's hydrogen, remember that only wants 2 electrons. If you do have any leftover electrons, go ahead and put them on the center atom. And if the center atom ends up without a complete octet, then use some multiple bonds, double bonds and triple bonds to some of the outer atoms to be able to give it an octet. So let's try using that process for these Lewis structures. Oxygen has 6 valence electrons. So if there are 2 oxygens here, your total number of valence electrons is going to be 12. So then I will connect these 2 oxygens with a single bond. This is the skeletal structure, step 2. And then the third step is to take the other 10 electrons. So we've used 2 out of the 12. We'll take the other 10, 2, 4, 6, 8, 10, and we start putting them around the outside atoms. This one doesn't really have a central atom. And this oxygen has a full octet, but this one does not. So we'll go ahead and share this pair, make a multiple bond out of it, and we end up with a structure like this. It has 2, 4, 6, 8, 10, 12. It has the correct number of valence electrons. Each oxygen has an octet, 2, 4, 6, 8. 2, 4, 6, 8. So this is a good Lewis structure. So for CO2, we have carbon with 4, oxygen with 6, and the other oxygen with 6 valence electrons. So we're going to need 16 valence electrons total. Let's make a symmetric skeletal structure. So this has used 4 of the electrons. We still have 12. 2, 4, 6, 8, 10, 12. So I put those lone pairs around the terminal atoms. Now the oxygens are looking good with complete octets, but the carbon only has 4 electrons around it. So let's go ahead and share from each of these outside oxygen atoms. And we end up with this kind of structure for carbon dioxide. Now the carbon has 2, 4, 6, 8, and each of the oxygens has 2, 4, 6, 8, 2, 4, 6, 8, and the total valence showing 2, 4, 6, 8, 10, 12, 14, 16. So we have the correct number of valence showing. All right, so let's figure out the total valence for the carbonate ion. We have 4 from carbon, 3 oxygens, each having 6, and we have 2 additional electrons. That gives a total of 24 electrons. We'll use 6 of these to connect the skeletal structure. So we have 18 left. That fills up octets around all of these terminal oxygen atoms, 2, 4, 6, 8, 10, 12, 14, 16, 18. And the oxygens have octets now, but the carbon does not. So let's just go ahead and borrow 1 set of electrons and make a multiple bond to one of these oxygens. So now all of the atoms have complete octets. There are 24 valence electrons showing, which is what we need. And I just put it in brackets with a -2 to show that this overall structure has 2 extra electrons with a -2 charge for this carbonate ion. So let's look at this next structure, silicon tetrachloride. Silicon has 4 valence electrons and the chlorines each have 7. There are 4 of them, so that brings it up to 28. Plus 4 makes 32 valence electrons. I went ahead and formed a skeletal structure with single bonds that used up 8 of the electrons, so we have 24 more. When I put these electrons around the outside atoms, the terminal atoms, that uses up those 24, and it also gives all of the atoms a full octet. So that is looking good. So nitrogen has 5 valence electrons and hydrogen has 1, so there's 4 of those. That brings it up to 9. However, there's a positive charge, so we need to take away 1 electron and have 8 total valence electrons here. That's what makes it positively charged, because one of these 9 electrons is missing. And then when we put together our skeletal structure, it actually uses all 8 of those electrons, and we are pretty much done except to show that it has a positive 1 charge. So again, here nitrogen has 5, so our total valence would be 10. Only 2 of these are used to connect the nitrogen with the skeletal structure. Alright, and then the rest are used up now. 2, 4, 6, 8, 10 valence electrons showing. So this nitrogen looks okay. This nitrogen looks way short. So we're going to have to share a few more pairs, get a multiple bond going. And so this is looking a lot better. Each of the nitrogens has a full octet now, and still we just have the 10 valence electrons showing. I wanted to point out some exceptions to the octet rule as you're drawing these Lewis structures. Not every Lewis structure is going to be able to have every element, every atom in the molecule obey the octet rule. There are some species called free radicals that have an unpaired electron. They have an odd number of electrons, and so that is not going to be able to have an octet around everything because it's just not possible to do that with an odd number of electrons. We are not going to be dealing with those in this class, nor are we going to see too many of these electron deficient molecules. So beryllium only having 2 valence electrons and boron only having 3 valence electrons sometimes forms a structure where the boron or the beryllium atom does not have a complete octet. Again, we're not going to deal with those too much, but one thing that we are going to see a few of are these hypervalent molecules. Once you get into the 3rd period of the periodic table, you have elements like phosphorus or sulfur. They have 3p orbitals that they are filling in their electron configurations, but there are some empty 3d orbitals for those elements as long as they are in the 3rd period or larger. And so since they have some open 3d orbitals that are empty, they can actually fit more than 8 electrons around them, and we'll be looking at some structures where it's actually more favorable for the phosphorus or sulfur to have more than an octet, and that would be called a hypervalent phosphorus or a hypervalent sulfur.